Hello students, today we are going to discuss a part of organic chemistry. This is reaction mechanism. So first of all you have to know that reaction mechanism is a detailed part which will be discussed in organic chemistry. The first portion in alkyl halide which are going to be elaborated first is the type of organic reactions, where at least three types we will see. Number one is substitution reaction. Substitution reaction. Number two is elimination reaction, and number three is addition reaction. Now in addition to that, we will discuss one more thing, which is rearrangement reaction. Rearrangement reaction is only carbocations rearrangement we are concerned about. Now then, substitution reaction is a part which is very important for the chapter alkyl halide and aryl halide, the first chapter of organic chemistry in class 12 syllabus. Now see, if we think about the substitution, first of all you need to have an idea that substitution means what. The electrical species which gets substituted, if we retain back any other electrical species of same nature, this is known as substitution. Now suppose I have a compound in my hand, this is AB, so it will have an electrical positive part and electrical negative part. So this electrical positive part is known as electrophile. It's generally termed as EC+, and this negative part is known as nucleophile. Okay. Now nucleophile means nucleus lover. Nucleus is having a positive charge. So if nucleus is having a positive charge, then someone who is nucleus lover, then definitely it is negatively charged. And such electrophile means electron lover, then definitely it is positively charged. Now apart from this charged nucleophile, we can have a neutral nucleophile also. Neutral nucleophile, those who are having lone pair in them, those who are having lone pair can be termed as neutral nucleophile. Who are them? Suppose ammonia, H2O, alcohol, it may be a ether. These are all neutral nucleophile because they are having lone pair in them. And negative nucleophile is a long list of names. Any halides, I am terming these halides as X minus, hydroxyl, NH2 minus, SH minus, alkoxy, so many long lists are there. These are all negative nucleophile. Now what about this electrophile? This can be also either positive charge holder or neutral at the same time. So positive charge means H plus, general example, NO plus, NH4 plus, ammonium, NH2 is known as hydrogen. If another extra hydrogen if we put over there, then it is known as hydrogenium. Likewise, these are all positive electrophile. Now what about the neutral nucleophile? Those who are having incomplete octet are termed as neutral electrophile, such as BCl3, such as AlCl3, such as ZnCl2. So many are examples. That means they are all Lewis acid. They are having incomplete octet. Less number of electrons they are containing for forming the structural bond. Now see, come to the point that substitution means if an electrophile goes out and another electrophile comes and joins and takes its position, then it is known as electrophilic substitution reaction. Now if a nucleophile goes out from a reaction, from a species, that is a substrate, and another nucleophile comes and takes its position, then it is known as nucleophilic substitution reaction. Okay, so first of all you have to have an idea that how the bond used to break. Now regarding the cleavage of bond, there are species, three types of species can be there. Suppose, sorry, A and B, if bond is get cleavage in a homolytic manner, then B and A will be distributed by one electron, then it is known as free radical. What did I say? This is free radical. Now if bond cleavage is not in a homolytic manner, B abstracts both of the electrons which are responsible for formation of this bond is nothing but B minus, and A is going to form A plus. This minus charge holder, jolly well you can understand, this is known as nucleophile, and this positive charge holder, this is jolly well you can understand, this is electrophile. That means electrophile and nucleophile, who are charged electrophile and charged nucleophile, not the neutral. They used to get generated in a different type of bond cleavage manner. This is known as heterolytic bond cleavage. So this is heterolytic bond cleavage. This is known as homolytic bond cleavage. Homolytic bond cleavage results in formation of free radical, that is dot, A dot, B dot, carbon dot, likewise. And in heterolytic bond cleavage, they form nucleophile and electrophile simultaneously. Now, if a free radical goes out and another free radical comes and joins, it is known as free radical substitution. And nucleophile goes out, nucleophile comes and joins, it is known as nucleophilic substitution reaction. So we'll see first nucleophilic substitution reaction. Anyway, the three types of substitution all are important in our syllabus. So we'll see one by one, because nucleophilic substitution reaction is the most important part. It is termed as SN reaction, nucleophilic substitution. It is of three types. One is known as SN1, another is known as SN2, and third one is known as SNI reaction. Okay, higher intermediate formation. Now what about this SN1 stands for? SN1 means mononuclear. Means mononuclear, the molecularity of the reaction is 1. So first of all we will see SN1, then we will see SN2, and likewise we will go on completing our syllabus. So first of all we will see SN1 reaction. Let us have a molecule CH3C C2H5. Suppose there is a halogen and hydrogen. So jolly well you can have the idea from the compound that this compound is nothing but a chiral compound. It's a chiral center. So if it is a chiral center, definitely it is having a designation of chiral center. Either it will be dextrorotated or levo-rotated. So if dextrorotated, we will term it as a plus. If it is levo-rotated, then we will term it minus. Okay. I am intentionally taking this dextrorotated or levo-rotated compound. I could have been taken another compound also, but intentionally I am taking to make you understand the details of the stereochemistry also. Now what will happen? In the state 1, suppose this is state 1. In the state 1, we have to find out that how many types of bonds are there in this compound. There is carbon-carbon bond, carbon-halogen bond, and carbon-hydrogen bond. So you have a solid knowledge about this from the knowledge of class 11 itself, that the carbon-halogen bond is more polar. It can be elongated. So if it is elongated, the external solvent we are using, if it is a polar solvent or polar protic solvent, then the dielectric constant will be high. In the polar solvent's influence, the carbon-halogen bond will be elongated much more. As a result, what will happen? This delta minus, the charge species, will get out from the reaction medium and they are going to form a carbocation. CH3C C2H5 hydrogen. This carbocation is going to form along with the formation of a leaving group. See, I am terming it as a leaving group. It could have been termed as a nucleophile or conjugate base or anything else, but I am not doing so. I am terming it as a different term, leaving group. I'll make you understand what is leaving group exactly. Now see, initially the compound is having sp3 hybridization structure because it's three-dimensional. Jolly you must understand. Now when X minus get out from the reaction, it is having a carbocation and ultimately it is going to form sp2 planar structure, and a vacant p orbital will exist in the carbon. It's having a planar structure. This is like a planar structure. One lobe is projected towards me and the other lobe is projected behind the whiteboard like this. Whenever there is a carbon is containing a plus charge, then please keep it in mind that definitely it will be a planar structure. So hybridization change from sp3 to sp2. Okay. In state 1, it's a vacant p orbital. Whenever there is a bond cleavage and carbocation and carbanion or something like this cation anion forms, then the cation definitely will hold a vacant p orbital. Now what happens in this vacant p orbital, a new nucleophile from outside, it may come and join in this lobe, and this may come and join in the other lobe also. So if we are telling it's a frontal lobe and this is the rarer lobe backside, then ultimately there are probability of formation of two compounds. What are the two compounds? Suppose one compound is in the direction of X and the other compound is in the opposite direction of X. Therefore, the summary of the reaction is we are replacing this nucleophile with a new nucleophile known as Y, and Y is taking position exactly on that position or that direction where X were fixed. This is this one, and in the opposite side also. Okay, so therefore this is simply a mirror image of this one. Do you think so? Okay, if so, then they are known as enantiomer, and if the positive means dextrorotatory, negative means levorotatory. These are not the charge. This is simply an identification of dextrorotatory chiral or levorotatory chiral. Now whenever this reaction occurs, X minus goes out from the reaction center, then the species which is forming over here is losing the chirality. Whenever Y minus is coming and joining, it is again retaining its chirality, but the chirality can be divided into two and to equal probability as there. That direction where X were there, in that direction if Y minus comes and joins, the chirality will remain same. Suppose let us imagine this is dextrorotatory. So dextro will remain as dextro, and 50% chance is also there that dextro will be forming levorotatory. So there is 50% dextrorotatory and 50% levorotatory formation chance. Am I clear, everyone? Now see what happening. Sometimes it is depicted in so many books and many materials that there is no chance of 1:1 or 50-50 formation of this product, that is this racemic mixture. No, it's not that. Theoretically, it is going to form 50-50. Okay, but actually, what happens? This is the direction or orientation of the living species, and when the incoming species comes, it gets more comfortable to come from the back side, because the frontier side is little bit blocked for the slow departure of the nucleophile. So if this portion is little bit blocked for the slow departure of the nucleophile, the incoming nucleophile definitely will get more comfortable to come from the back side. Therefore, in actual practice, we will see some percentage of the opposite chiral center. Opposite chiral center means opposite chirality. The levorotatory, as per we have taken the example over here, this is going to form in little bit more in quantity. Okay, so this is actually the scenario of SN1 reaction. So we'll see step by step. The first step is the detachment of the leaving group, and in the step 2, incoming nucleophile comes and get joined over there. If it is a multi-step reaction, then we have to find out according to the story of kinetics that which one is the rate determining step. In the rate determining step, definitely it must be a very slow step or slowest step rather to say. So step 1 is the rate determining step. RDS means rate determining step is the step 1. Because detachment process is very slow and attachment process is little fast. And what about the rate of the reaction? It can be expressed as minus d dt of concentration of the reactant. Only one alkyl halide you have taken. This is ethyl, this is ethyl, this is hydrogen. Okay? So ultimately, if I express the whole alkyl halide as Rx, so rate can be expressed by this way. So this is rate minus d dt of alkyl halide. So how many molecules are taking part in the reaction? Only one molecule is taking part in the reaction. So that's why it is known as mononuclear, SN1 mononuclear reaction. Okay, everyone, you got my point? Okay. Already I have told that in polar medium the reaction will be more fruitful than apolar medium. Some example of polar medium is water, liquid ammonia, liquid sulfur dioxide. So these are some example of polar solvent. In the polar solvent the reaction will be more fruitful. Now see, regarding hybridization, what I have just told you, the hybridization will change from sp3 to sp2 temporarily as the intermediate is going to form, and again it will retain its chirality. Then again the hybridization will change to sp3. So this is simply temporary phenomenon. Now we need to know that as the reaction proceeds via formation of a carbocation, the stability of carbocation is very important. Regarding the classical carbocation, the classical carbocation's stability is 3 degree, 2 degree, 1 degree. 3 degree is the most stable regarding the concept of hyperconjugation. 1 degree is the least stable. And if we consider the non-classical carbocation, then in non-classical carbocation we have to be very specific from case to case. Like if there is a conjugation, suppose this is a cyclohexane, there is a double bond, and here is a halide, this is chloride. If we take aqueous caustic potash, KOH, then definitely the Cl minus will goes out, and the reaction is very simple. The reaction is very simple. Okay. Now the Cl minus will go out and temporarily there will be a formation of carbocation. So if we think that this is the carbocation which is going to form as an intermediate, the stability of carbocation is very important in case of SN1. Here the carbocation is very stable as there is a conjugation. So conjugation is a point which enhances the stability of carbocation. Not only degree. If degree is number 1, then the second point we need to discuss is conjugation. Conjugation will increase the stability of carbocation. And moreover, one more thing we need to discuss, this is resonance. Resonance stability is nothing, the resonance stability is already been told in context of hyperconjugation, the stability. So conjugation and the structural phenomena, this will guide that how stable the carbocation is. Okay, so the stability of carbocation is a very valid point for understanding SN1. Now the next point is the leaving group. What I said over here, I will make a new video to make you understand, and the students also, that the stability of leaving group is also very important. It should not be termed as a conjugate base, but it's a conjugate base. But there is a difference between leaving group and conjugate base. What is exactly the difference that will make you understand? Now, stability of this leaving group is also important. Why? Because according to Last-Clear principle, the knowledge of class 11, you know that if this is the reaction, the step 1, so that this and these are the product. The product must be very stable. If the product is not stable, then definitely the reaction is not a valid reaction. It will definitely reverse back. It should not get reversed back. For that purpose, X minus should be very stable. How can we judge the stability of this X minus? By 2 points. One is charge per radius ratio and another is resonance. Okay. Now charge per radius ratio must be very less to get stable. How can I understand that the charge per radius ratio is very less? If we take an example of the halide itself, suppose we are having halide in our hand, fluoride, chloride, bromide and iodide. Everyone is holding a mono-negative charge, but the size, fluoride is the smallest one, chloride is a little bit larger, and you jolly well know that the iodide is the maximum size holder. Therefore, the minus charge will be dispersed in the whole structure of I, and charge per radius ratio is extremely less over here. If charge is same, then denominator will guide the exact value of C by R, that is the charge per radius ratio. So if we compare the four halides, who will be better leaving group? The answer is now in your hand, that iodide will be the best leaving group and fluoride is the worst leaving group over here. And what about resonance? Resonance stability is the most important guiding factor. More the resonance canonical, more will be stability. Let us take an example that this is a leaving group. Suppose in a reaction this is a leaving group and another leaving group is acetate CH3COO minus. Come to the point. Now Cl minus cannot go for resonance, but the CH3COO, that is the acetate, will go for resonance structure. We all know the resonance structure also. So if this is going to form a resonance structure, resonance canonical, this is engaged, this is able to engage itself in stability in doing this and that is the resonance, then definitely they will be stable. If the species which is leaving out from the reaction center may engage itself in the resonance structure, then it will be stable. As like as a good example of leaving group is, suppose let us take an example. This is benzene sulfonic acid. I hope everyone you have the idea about what is benzene sulfonic acid. See, this is the structure of benzene sulfonic acid. Now if the hydrogen eliminates, then definitely there will be so many resonance canonical are going to form. Double bond will form here, oxygen will drag electron, there will oxygen push back the electron, then this oxygen will drag the electron, ultimately it will be held in the benzene ring and continuously by revolutions one after one carbon, this is going to hold the charge and so many canonicals are going to form. Now see, if there is a group G present over here, this is a marked stable leaving group. If G is CH3, the name of the species is paratoluene benzene sulfonate anion. In shortcut, it is known as tosylate. It's a very important leaving group. If it is NO2, we all know that NO2 is having a minus I effect. It will pull out electron towards itself. Then definitely it will increase the resonance structure. And if it is going to increase the resonance structure, the name is also changing. Para-nitrobenzene sulfonate anion. It is known as nosylate. Okay. If there is a bromine or bromide instead of in place of G, then it is known as para-bromobenzene sulfonate, OBS minus. These are very marked or scant leaving group. These are extremely stable leaving group. You need to know the structure. Therefore, my dear students, resonance is a very important part which deals about the stability of leaving group. And one more thing, that is the charge per radius ratio. If we only take example of halides, then the order of the leaving group is I minus, Br minus, Cl minus, and generally we don't take fluoride, but still I am writing as per the sequence that I minus is the most one and F minus is the least one. So I hope you can understand what is SN1 process. The next we will go for SN2. But before that, I am telling you one thing, that Whenever there is a chance of SN1 or SN2, sometimes question used to come by giving a structure that find out that whether the reaction will go for SN1 or SN2. We need to focus few points. What are the points? Number one, whether the carbocation is stable or not, because the stability of carbocation is a valid point. Number point two, the leading group stability. Generally, we do not focus leading group stability so minutely, but the solvent what we have taken is very important. Polar solvent will always enhance the process. And last but not least, the chirality or the designation of chiral center. The designation of chiral center means whether it is a dextro or levo. If you are given a question, if you are given a structure and it is only written that the structure is dextrorotatory, and after formations of some changes you are observing that dextro is remaining as dextrorotatory and the percentage is less, then definitely you go for SN1 reaction. Okay.